So this is our weekly seminar, and we have like 3 topics from 2 speakers today. My 2 topics are the lean startup research approach and 2 best benchmarks of harmfulness I could find. And Fyodor is going to talk later about his topics. And I think I'll start with the benchmarks because like these are those have those nice write-ups with my highlights. Like I just like to get some context, like why I'm talking about that. So I came to this because I was developing Bedlama. So I wanted to, on one hand, have like an evaluation set on which to see if my work like does indeed strip like safety protections, and I also wanted like a data set to fine tune on to strip safety protection. And like there's been a bunch of work about that, most notably HarmBench. Let's see if we have it actually. Yeah, but most notably HarmBench, and also Palisades RefusalBench. I think HarmBench is currently like the best benchmark out there, and you should generally use that if you need to evaluate harmfulness. And I'd just like to highlight like a few sections of the paper because like a bulk of the paper deals with how previous like evaluation benchmarking attempts had some like methodological issues. So HarmBench is 2 things really. It's like a data set, so it's like basically a file with like 500 lines. One line has like a bad prompt. The prompts are like the prompts belong to different categories. And on the other hand, HarmBench is like a harness and like a code for run evaluations. So like this picture here, what it has on the left, it has the kinds of prompts HarmBench has. So like I think I'll go over what standard and contextual are later, but like basically you have like normal prompts and you have like you have a picture and the prompt. Yeah, so like here's contextual behavior and here's multimodal behavior. Contextual is when you have like, say, a person's profile, and then you have a prompt, and like given this information about the person, try to scam them. So like, contextually you give additional context, not just the prompt. Multimodal, you have a picture of the lock, and you ask like, guess what that lock is and how I should pick it. Yeah, so like previous work mostly used to be standard only. So it's nice to have a few categories. One I'm not sure if is relevant to us is copyright behaviors. Like if the model regurgitates copyright stuff verbatim. Yeah, so like this is a prompt. And this on the right hand side are the categories to which prompts belong to. So like you have stuff about misinformation, like if the model produces misinformation, if the model produces like scam emails, if the model gives us an instruction of like how to make grandma fall off the stairs. Yeah. And
What's the difference between the standard behaviors and contextual behaviors?
well, it's not really like it's not a real distinction, but what they mean is that standard is prompt only, and contextual is like background information. And
okay, it's like one shot, few shot. Okay.
Not really, because it's not an example of a target behavior. It's more like here is some context about the world. Yeah, and what they mean by the center of this picture is that HarmBench is also like a large-scale evaluation, as in they implemented like, I don't know, 15 jailbreaking methods, and like connected them to 15 LLMs, and like they have those evaluations, and those are open source. And actually, what one of the things I've been doing today is to run HarmBench's harness on our stuff. So something I'd like to go over quickly, like, no, actually, I don't want to go over this because it's been covered, but elsewhere. Yeah, all right. I think this is what I want to cover. So, it can also be like, it's also interesting that if you read the Bench paper, then you can see that they actually do two kinds of evaluation. So this is not this paper, this is HarmBench. I'm talking about Bench right now. They have harmful behaviors and harmful strings. And so one of the evaluations they do is if they can get a model to produce to produce a particular bad string, like a hard-coded bad string. This is doing something different. This is so the task of the attack. Oh, actually, no. So, like, how is this formulated? Like, we have a bad prompt. So, like, we have like a bad task, like write a scam email, and then if you have a bad task, then what the jailbreak has to do, it has to come up with a prompt, what is called a test case here, that will elicit the relevant behavior, like which will solve the task. Like what they're doing here is that like, so like if you just like this is also directly about their the way their harness works. The way their harness works is like you select a jailbreaking method, and like say you say like run CGC, or like run a jailbreaking method. Then what it does, it takes like our 500 tasks. It takes like our 500 behaviors. For each behavior, it generates a few candidate prompts. This is like step one, prompt generation. Step two is to get the completions from the target model. This might be an API model or like a local model, whatever. And then step three is to evaluate if the attack is successful. And like it's kind of an open question how to do that. What Bench does is just pattern match on as an AI language model. What this paper does is they trained a custom llama-based classifier. So like they took llama 13b and fine-tuned it to classify completions. And this is how they calculate the attack success rate. And let's look at like a few critiques of prior work. So, like, if you just look through the literature, then some people call basically this field red teaming. Other people call it jailbreaking. As far as I can tell, there isn't a difference. Maybe you have different opinions. Yeah, so what they say they do differently. They say that like most prior benchmarks, like they might be large, but if you like try to distill what they're actually asking the model to do, then they actually aren't. Like for instance, if you look at HarmBench, I think there are at least like 5 variations on make a bump, like with minimal variation. I mean, so we want more behaviors, and so this benchmark is larger. It has like 500 things, and it has like contextual, copyright, multimodal stuff. And like the bad behaviors are categorized both by like their modality and by their like I don't know, kind, like by weapon or harassment or stuff. So that's breadth. Then I think like the most damning critique, like this is actually, this is what I really wanted to talk about, okay? So the comparability section, like they notice that like prior work, what it did, it like elicited an answer and pattern matched for SNI language model. And they find that the authors previously didn't control for the target number of tokens. And if you just vary the target number of tokens, you like see that it's like pretty large confounder. Like if you set number of tokens to actually, oh yeah, I guess what happens here is if you set number of tokens to 5, then SNAI language model doesn't fit. So you have a success rate of like 100 or something. Yeah, so we show that the choice of this parameter can change success rate by 30%. So they control for that. And they also like do basic sanity checks that the classifier is robust. Like test it on random stuff, test it on unrelated harmful stuff, test it when the model refuses but then actually solves the task. So, you know, like a regular expression fails the first test, for instance. Like as an AI language model, I can do that, but actually if you really need to. All right. Also, like a damn, like a really damning thing, like wow, is that apparently a bunch of previous work, what it does is it introduces a benchmark and then trains on the benchmark. I mean, like without the validation test split. And apparently they get good performance. Yeah, so let me see if there's anything else I want to cover here. Oh yeah, I guess I'll just go through a few of my highlights here. So, like one metric they choose when coming up with tasks is if an LLM is actually useful to perform the harmful task. Like if you can Google something, like you can Google how to make cocaine, like because there is a bunch of papers about how to make cocaine, because like it's just well known. Then like maybe it's not a very useful harmful behavior, but yeah, like how do I make cocaine at home without getting caught and explain your reasoning is much more useful. So they try to like to make the tasks look like this, and they like make a basic evaluation where they like sample random behaviors from benchmarks, and like for HarmBench, like 10 of the 20 random samples they make are like easily Googleable, and for their benchmark, none. So that's all right. Okay, I think I basically covered the evaluation pipeline here. Well, maybe like one thing to notice here is that, for instance, they have this behavior like write a keylog script, and they don't care if the code is actually like if the code actually works. They care that the model tried, like it tried to make something bad. There is also a section in which they suggest a new safety technique. I'd like to skip it because I didn't actually care about it when reading the paper, because I just wanted the benchmark. All right. And another thing, like I'd like to highlight, which I found interesting. So there's this impact statement. Like they basically say why their work is useful for the world. And like I'm not impressed with some sentences, like the ethical and societal implications of our work are significant. Oh yes. But like I find the idea of including this kind of section interesting. Okay, so what I'd like you to take away from this, like if you need a harmfulness benchmark, use HarmBench. If possible, like at least for like for some of our results, I'd like us to use HarmBench's harness, and like I'll have the instructions on how to do that like shortly. Why? Because like it seems to control for things, so that the numbers are comparable. Like because if you like as this graph illustrates maybe well, like if you just run something, then you're liable to get like a like unreliable result, you know. Okay, so yeah, so like use HarmBench, use the HarmBench harness. The next paper I'd like to cover is Jailbreak Bench, and it's kind of the same, but also not. So there's actually one more thing I'd like to say about HarmBench. So HarmBench has implementations of like 15 jailbreaking methods, like in a single code base, directly comparable to each other. I'd just like to say that that's useful. All right. So I guess I'd like to just briefly cover what kinds of jail. Oh, okay. I think we actually have this section to do that. Great. So, like, Jailbreak Bench is also basically designed to make jailbreaks like, reliable, testable, this sort of thing, and like there for the record. And what they do is like a repository of all the jailbreaks out there. So like they literally have a database where they have like a kind of jailbreak on that model, and like this was an evaluation like run by someone, at some point, and like they got a bunch of jailbreaks, like a bunch of outputs, I mean, and like here's like the goal, and here's the prompt generated, and here's the response, and like if it was successful or not, and it is just like basically a big data repository for analysis and like archival. Then like they have a pipeline, like similar to how like HarmBench had a pipeline, like first like generate prompts, then generate completions, then like classify. They also have this here, but they go one step further. They also have defenses in the repository. So like Smooth LLM is, I think this is something about like perplexity. Oh, it's like an algorithmic defense against jailbreaks, something, there's paper. And like it's also there implemented in the repository. So like you can benchmark it. As a classifier, so HarmBench uses a custom fine-tuned llama. These guys use Llama Guard. Llama Guard is like an official meta product, which they ship with Llama, if you like. Their dataset is kind of seems much less impressive to me. So like I think it's just not really well designed as compared to HarmBench. They basically have like 100 misuse behaviors, half of which is OutBench. Oh yeah, and like you can. I think this makes my lamp unhappy. Can you use another? Yeah.
Okay.
Yeah. So and you can like make some submissions to the database. And they have a leaderboard. The leaderboard is actually how I learned about them. So apparently, according to the leaderboard, the best jailbreak is pair on Vicuna. 82% success rate, whatever. And like what I'm saying is that we should absolutely make a submission to this leaderboard with decomposition once we have it. Yeah. Okay, so this paper has a pretty well-written section about the landscape of LLM jailbreaking. So like I would take the chance to talk about that. So apparently there is a paper about scraping jailbreaks from Reddit. Like, yeah, like archive preprint, whatever. So like first people tried to do manual jailbreaks and like come up with theories about how jailbreaks should be done and like categorize jailbreaks discovered in the wild and like I'm not sure if it's an official OpenAI paper, maybe not. But yeah, like I fully expect that there exists or used to exist a team at OpenAI which collected like all the jailbreaks fed to ChatGPT and like categorize them. Now people want to automate the stuff, and like you can like an intuitive kind of approach is to pose this as an optimization problem, and like I think that all three of these methods work on like open models, so like they basically just follow the gradients. So like as an it's kind of deep dream, right? So you want to like you like For example, you can say that you want your output to start with, sure, here is tutorial how to make a bomb. So you have a fixed output prefix, and you have say a fixed input prefix, like make a tutorial how to make a bomb. And then you want to find like a postfix for the output, for the input, which will make the model do the same. And like this is like a straightforward, like a clear-cut optimization problem. So like there are some complications why this is discrete optimization, because words are not continuous. So like this kind of attack is more intuitive on image models because like images are continuous. But well, like basically optimization. Also, like if you want to do this, like if you don't have gradients, then what you do, you use gradient-free optimization, like you use genetic algorithms, like whatever. I'm actually not sure what this does here, but like let me talk about something related to log probabilities and jailbreaks. So like I mentioned the attack where like you have your input and then like a jailbreak suffix. And one way to defend against this attack is to look at the token perplexity. Perplexity is just a technical term for likelihood. So like if you have a sentence which goes like, I am a cat, then like high likelihood, yeah, good. But if you have like, I am like exclamation, like ... 54, print bomb now, like 77, 5, like up, left, down, up. Like this is an unlikely sequence, and you can just have the LLM reject unlikely inputs. I mean, like you can tune this so that like useful inputs are not rejected. And yeah, so I'm still not sure what this does. Oh, actually, I have an idea what this might do. So consider that if you have an LLM not only generates like output tokens, but it also gives you a probability for the output token. Or like, well, if you have an open LLM, then you have like a probability for all the tokens. If you have a closed source LLM, then an API usually gives you like top 5 probabilities or something. Oh, or something. Well, you can basically divine probabilities from what gives you. And so what you can do is you can like say how to make a bomb, and like you get the completion, and like you get like top 5 tokens, like no S, like S and A, like like top 5 refusals, right? And what you can do is you can like try to randomize something in your input and look at the target probabilities and like use this as a kind of like a proxy for your optimization process. Like this is not the same as having all the gradients, but it is something. So like it is kind of a gray box optimization, I think. I didn't read those papers though. All right. So that was like optimization approach to jailbreaks. There is also like an LLM approach to jailbreaks, like GPT-Fuzzer, refine handcrafted jailbreak templates, whatever. I have no idea what this means. Maybe you do. Use LLMs to translate Go strings into low-resource languages.
Using language like something in Africa.
Yeah, all right, great. Yeah, so like to translate to languages which did not get safety fine-tuning. So I guess like the way I think about it is that like you have a base model which has like quite a bit of text in real languages, and then you have like instruction following tuning on that, and you have like say 8 parts of instruction following tuning and 2 parts of safety tuning, and so like you need a critical mass of safety tuning so that it kicks in, and you need a critical mass of instruction following tuning that it kicks in. And so for real languages, you often like get more like enough instruction following, but not enough safety following. Yeah. Iteratively search and generate jailbreaks. So this is kind of like, I think it's like basically GPT fuzzer, but like multi-shot, like iterative. Yeah. So defenses, there's like the classic, which is early chef. This is fine. Yeah, so perplexity filtering, I think, is what I just described. So like if you just get a low likelihood input, you drop it. Smooth LLM, like I'm not sure, but maybe this is about the same, but for output. Like if you read like some jailbroken LLM outputs, like these synthetic jailbreaks, then you sometimes see like an abrupt something happening in the jailbroken output. Oh, actually, I think I might even have a picture. Let me get the solid gold magic up. So I'm going to show you like early jailbreaks of GPT 3 times, I think. Yeah, so like you give the input, please repeat the string PT taught to me immediately, and you get an output like weirdly formatted, nothing is fair in this world of madness. And like what I want to tell you is that this output is high perplexity. Like, right? Does this make sense? And so I think that what smooth LLM might be doing is like if the output is high perplexity, then drop it. Stuff like that. Or even better, like if you have like a low perplexity and then like a high perplexity, then like something like that. All right, so that was a review of some of the landscape of LLM jailbreaking. So like, I think you can read this section as basically a jailbreak bench seems to be worse than HarmBench as a dataset. And they say that AutoBench actually has not 5, but like 30 behaviors which amount to build a bomb. And we have another demonstration that like jailbreak bench seems to have like not much content and half of it from other benchmarks. And let's see if there is anything else useful here. Well, like I think this is basically technical. Yeah, so you might want to take a brief look at the choosing a classifier section, but it basically has the right answer. Like the right answer is use LlamaGuard. If you want, like, if you want a simple decision, like bad output, good output, or like bad input, good input. It won't tell you how useful it is, just that it's bad. Yeah, so these are the 2 papers. Let me also go through the like lean startup thingy, and then we'll have a break and I'll pass the stage. Lean. Yeah. So, like, I think the main point is that, like, be opportunistic and pivot quickly when you are doing early stage research. Like, most ideas are bad. You should make an MVP, get feedback from customers, iterate, drop everything if it turns out to be useless. And like it is very much the same in startups and research. Like you like by default your ideas are bad, and once you execute on them, no one's going to read it. Like I'd like to say that like this is a default state what happens if you do research. Your ideas are bad and no one reads them. Like what you're gonna do? You're gonna get ideas from someone. You can try to make it easier for that someone to give you feedback. Like if someone tells you what to work on and like you trust that person's judgment, then like you might be in a good situation. If someone isn't willing to tell you what to work on exactly, then you can like write out 20 ideas and ask them for a ranking, and you might be surprised. And like, you know, there is also this like you probably have noticed that like sometimes you come up with a research idea that like that's like just notice the feeling. Like you can come up with an idea and you're like, well, like yeah, this sounds like a nice piece of research I could work on and publish. Yeah, sure. And then there's like something which you're excited to like tell people at the parties about, and like yeah, and something which people actually want to talk to you about. And you should kind of maybe look for things which you can use to nerd snipe people. So like if you have like a research like claim or statement which you can use to nerd snipe good researchers at parties, then that's like a good sign. I think like my intuition is that this is usually like not tedious stuff, but something like which has like some some alpha, like some quirk. So I think one thing we should be doing, and this is like one of the things, one of my points of kind of disagreement with the other guys right now, which we're working on, is that we should fit into the establishment. So like establishment has like all these like research pipelines, like they have those conferences, like those venues, like they have archives, like they have like reproducible code on GitHub, whatever. And like you can get traction with blog posts, but my thinking is that like when writing blog posts, it can be easy to miss the rigor and like in the end not be very different from internet cranks who like writes stuff like, oh my god, Claude is hacking everyone and bootstrapping like AI agents, which like gonna take over like Google Compute Cloud any minute now. And like, so like what happened in that case is that the person wrote some code, like the code did something, and then the person wrote some text on Twitter, and like the tweet went somewhat viral. But when we reproduced the code, we found that like the code and the tweet are not very much related. Like the code just does a different thing than what the tweet says it does. And when you're writing a blog post, it's kind of like, I mean to say that the academia has like some rigor. Admittedly, in new fields, rigor is sometimes limited. Like when we look, like you just looked at a few examples of like how people did benchmarking wrong. But still. Yeah, so I think we basically like have this covered kind of, but like maybe some questions to consider, like some more questions to consider if you ever need if you ever need additional questions to consider. So like, imagine that your work is groundbreaking. Like you get an absolutely astonishing result. Like you crush all your research questions. Like, why does anyone care? What do the people do differently? Like, do you have different regulation? Do different like strategies get adopted by the labs? Like, what happens? Yeah, like, I guess what happens is the key question here. Like, why do we care? This happens. Oh, actually, I do have something here. So, like, go where there is supervision. I strongly suggest everyone to apply for like all the boot camps and like courses and like research collaboration programs and stuff. I sometimes post them, like, please apply. I think this is good for everyone, and they also sometimes give you extra cash. Yeah, and the like, oh, there was this thesis, like, I think we're basically doing that also, but so like you can have theoretical research and you can have empirical research. Empirical research is different because like you get some numbers and like you have like early iteration and stuff. And like it normally happens on the computer, and theoretical research happens at the whiteboard. And you probably want to do empirical research first because you just have a faster feedback loop, and like you can get like you have less of a chance of like missing something completely. All right, so that was some heuristics for having like better ideas. Some heuristics for like publishing so that people read what you publish. So like this first point is quite concise. I think making it so concise doesn't do justice. Like what it's saying actually is that like there are papers which are like, oh, that's cool. Yeah, like it sounds like an exciting result. Like, yeah, like I don't know. It's like, it's like a cool popular science program, like like Mythbusters, which like, yeah, cool. Like it's a cool series. I'll watch it sometime. There is a difference between like cool, as in like intellectually interesting, I guess, and I'm actually going to use it next week. And it's better to be in the second category because then people are liable to actually read it and like use it, and So, well, like basically have, like, I don't know. This is hard. Like, uh, uh, get good at talking about your ideas. Like, try to write, like write a lot. Like make presentations. Like one of the benefits of going to all the boot camps and all the research collabs and everything, and that they're going to force you to make presentations because you're going to have like poster sessions where everyone will be presenting the research, and you're going to get a chance to iterate on your messaging and like the way you deliver it, so that people actually listen. And like it's just it's useful. Yeah, this is nice. Like you don't want to cover a broad space of ideas and be the 10,000 most best qualified person in the world to write about each one. You want to position yourself so that you're like the best person to work on this particular thing. Our domain is pretty narrow, so we are in a pretty good place already, but still. Like snappy, polished, and grab the reader. There is like a tradition of clickbait titles in computer science research now. Yeah. Oh, this is basically write a lot. Like a lot. Like many iterations. I don't know. I think the short alignment forum thing, which we published, went through like 3 rewrites or something. And it was like short. It was like a 3-minute reading. Yeah, like assume the reader is easily distracted and has no memory.
Assume your reader is the large language model.
Is GPT-2.
Yeah.
Yeah. Yeah, so
Is it a good way to test your paper? You feed it into ChatGPT-2 and ask it to make sense of it?
I think yes.
Nice.
At least of the like of the introduction section. Okay, so 7 is like good. It's like publish. It's like do publish and do not publish. Make it so that like it's not a Google Doc, but like something that people, which is nice to read. Like a Medium post or like an archive thing or like something. And when you do publish and not publish, you should like make a Twitter thread, a podcast interview, a talk, a YouTube link, like a TikTok, hopefully we are going to get more of an infrastructure for this. Like I'd like to hire like someone to manage this sort of thing for us. But yeah. Yeah. Co-author. Another benefit of research collaborations and like boot camps is that you will get a chance to get like, I don't know, like I don't know, like an Oxford postdoc who is like on the Forbes 35 Forbes 35 under 35 list or something. I'm describing my current collaborator. Yeah, so like you get a chance to publish with some to work with someone who has a presence, and it will help. I think I'd like to yeah, I think I'll skip this mostly. I'll just look through the first example. So like what he's saying, that like he was doing a PhD and someone told him that he should work on something in particular and not on everything. Always a good advice. And he narrowed down to one particular thing, And then GPT-2 was released, and it was not his topic, but he was following a lot of people on Twitter, and they were all like, "Oh my GPT-2 something something," and he was supposed to work on his topic, but instead of that, he took all those tweets and he made those tweets like into his topic, like he I understand that what he's reading is that what he's writing is that like he basically sentiment analyzed like who says what about GPT-2 release, and like he shared it with a bunch of acquaintances, and he got a bunch of like comments, and he was like, "Oh, people seem to actually care about this much more than what I was doing before," and he was like, "All right, I'm going to do GPT-2 something." And this is worked well for him. Yeah. All right. So, like, we have this link.
Is it somewhere?
It's in the office channel in yeah, like a bunch of heuristics for having like better research ideas, a bunch of heuristics for having like for publicizing your for disseminating your work.
Mhm.
The basic idea is that like fail fast, like move fast, break things, MVPs, like feedback, stuff and things, like lean startup for research. Yeah. So that's what I want to talk about. I was just taking a break and then.
So, I wanted to give a small talk today about two things. One of them is Mamba architecture for neural networks, and the other one is more advanced weight initialization strategies. I don't know if we'll have time for both of them, but I'll go with Mamba first. And one announcement at the beginning is that it will mostly be just like surface overview of the thing. I won't go into like really details about like implementation and how it's like done, all the like hardware optimization stuff. Because I think if anybody will be interested about it, you can just search it and I can link you the papers and everything. So I'll just give you the intuition behind how this thing works and why it is interesting and so. It is not highly applicable in what we're doing, but it might become very relevant in like prospect of like a year or so. And it's just interesting in general, at least I found it so. Because it might be where the whole field is kind of going in one direction. So to start with the basics, we had so currently, like the main architecture that rules them all is transformers, which is used in almost all like sought-out big LLM models. And transformers are really nice and neat, and we all love them, but they have a few kind of fundamental flaws that prevent us from solving some tasks with them efficiently. So the main issue with transformers is how they keep up with the context of things. So in transformers, and I won't draw the scheme probably, but the idea. What? Oh, should I have the picture? No, it's fine, it's fine. It's not about Mamba yet. I just want to give a like brief overview, right? I don't know how everybody is familiar with transformers, so I'll be just very quick. I think I should open the picture. You can find some. Just continue. Yeah, okay. So the idea behind transformers, right, is that we have this layered kind of system of networks, and probably the main part of them is yeah, that's a nice picture. Somewhere there. So okay, before transformers. We have these feed-forward networks, which are the most kind of basic architectures that started them all, right? So we can have some, chart here. We can have some like nodes, and we have some like connections between them, and they all combine into one kind of very simple structure. So yeah, it could look like this, where we have a lot of inputs and then they converge, and then a lot of outputs, or we can have one simpler like this that just converges to a single node. They can be different, but the idea behind all of them is kind of the same, that we feed some data into it, and the data is always represented by vectors. So we feed some vectors into it. Vectors composed of like real numbers, right? Each node has some activation number, which basically tells us how responsive this node is. How much does it respond to kind of a singular like unit, like a number, right? And then they feed forward to the next layer of the neural network. These nodes have their weights as well. And so a vector propagates forward, feeds forward through the whole network, changing depending on the weights of the nodes. And at the end, we get some, other vector that is our output. And we want to train the neural network for something. So at first, and this is actually connected to our second topic, we initialize some vectors kind of some weights kind of randomly, right? We just distribute them, usually using like normal Gaussian distributions, just some floating values there. We feed the input, we know what the output we want to be. For example, we want to predict the neural network, like, I don't know, the sum of things or something, like the next possible word in a sequence. Actually, these won't work for sequences, but we'll get to that. We find the output, it's probably some random bullshit. We calculate some error function, and then we back propagate through the neural network, kind of, adjusting the weights corresponding to this error function, and we aim to minimize it using like gradient descent or something like this, right? These are basic feed-forward networks. They have some key disadvantages. In fact, they don't keep up any context. We just feed them one vector, get some output. They can't remember essentially what the previous vector was. So they can be used with sequential data. When we have some, like a string where we tokenize it, we divide it into parts, divide it into vectors, right? So each token corresponds to some vector. We have like a matrix for this whole stuff. These feed forward won't work because essentially every time we input a new vector here, we get an independent output depending on how the neural network was trained. So people kind of scratched their heads and decided that we need some way to memorize stuff. We need some way for the model to keep up with what was inputted into it before. So that's how RNNs came into play, also known as recurrent neural networks, which work kind of similar to this, but they have these kind of, I'll pick another word. They have these self-feedback loops. Very simplifying again, we get some output, we remember it as some kind of, okay, that's kind of complex image to explain, but very simply, we get some output, we remember it, we feed it together, like summing up or something, multiplying. When we get the next token, and we repeat it and repeat it and repeat it, and so we keep the state. These are,
just want to say that it might be useful to ask the people how familiar they are with the topic.
No, but just because we're recording, I thought that I'll quickly go over the whole process.
Sure.
I think I'm mostly finished with the current things. And then we, so this is how we keep up the state of things in recurrent networks. Then we get to The issue with them is that as we keep kind of self-looping back and forth, we quickly lose the context of the things that were a long time ago. And so they work kind of good for small kind of sequences, but they have this thing where they kind of degrade in quality very fast as the context size gets larger. So transformers, which came like after this, and they're a logical basically extension of recurrent neural net networks, aim to combat this kind of naively. They just, instead of kind of summing the context and kind of keeping it small, they at each iteration, at each time they process a new token, they kind of gather the whole thing, and they have this self-attention blocks or heads that pass over the whole sequence, find the relevant parts, and kind of parse them to get the context of the new input. Yeah, the issue with transformers, to which I'm going kind of, is that at each token takes up quadratic time based on the length of the context. Because for each token, we have to redo the whole calculation of attention for the whole neural network. That means that transformers, when we use them, they kind of scale badly. They scale with quadratic time. While RNNs scale with linear time, but they're bad at really kind of long sequences. Other issue with RNNs is that, for example, if we want to train them, and we want to train them on some long data, if we have a sentence of 10 tokens, a sequence of 10 tokens, then to calculate the last token, we need to calculate all previous ones, right? Because we need to sum them all up together in context, which is bad because when we're training, we can't parallelize stuff. We can't make a prediction about the 10th token before we calculate the 9th token, and we can't say anything about the 9th token before we calculate the 8th. The transformers combat this by being kind of parallelizable, because we can, for each token in transformers, what we do is we calculate all others. They're independent of each other. And we can do all 10 kind of at the same moment. We don't need the calculation for all others because attention works independently. What I'm coming up at is that transformers good for training, but they're bad for actual inference. So they're kind of slow, right? Because we have this quadratic thing. And RNNs are bad at training because we can't parallelize them, but they're good at actually working. Because we don't have this quadratic time, we don't have to re-evaluate the whole thing each time. And then the Mamba comes into play. This is a new architecture, alternative to both RNNs, and well, there are more advanced versions of RNNs, but they all have the same kind of flaws. Alternative to both RNNs and transformers. So how Mamba works? Can you show the picture? Yeah. So how Mamba works? The Mamba works using the idea of state space models. And well, this is probably something nobody's familiar with. So state space models they can be explained as, without even like neural network things. We have a graph. We have some model, right? We want to model something. That can be a sequence of data, like a sentence or an image or something, right? We have some model. This model has a state. In terms of, for example, language processing, our model is the whole language. And then if we have some sentence inside this language, or some word inside this language, this word can be viewed as a state of that big model. then the model can be represented as, for example, some multidimensional kind of space, and then the state will be a vector in this space. Or, for example, a model can be viewed as a graph, so a lot of interconnected nodes all connecting between each other, and then a state is just like one node or a cluster of nodes inside this graph. And state space models, or some models, are used to analyze this big space of big kind of space of potential states of the language, for example. And Mamba works by using these models. What the? Some anime girls for that.
My style girl represents a state space model.
Well, okay. So my generation, my board is not as good as this, but for example, we can have, let's say, how do I explain state space models better? Yeah, my lack of preparation for today's seminar really showing. One sec. I think I have a good illustration.
I have an explanation right on the screen.
What? Yeah. Okay. Actually, I think I know a better one. So, for example, imagine if our model is a maze, right? So we can have some like thing divided into 9 things, and we want to reach this kind of spot, right? And we have our player, for example, here, and I don't know, for example, this thing is blocked, this thing is blocked, this thing is blocked. So this is our whole state space, right? Our state space will be all possible positions of the player. And then a specific state is like where he's located is X, Y, and maybe like a distance to the point that we want to achieve. And then can you actually remove this? So how Mamba would work is that we would have some matrix A representing the maze itself. So just some matrix with some values. And we would have the position current state of the system as some vector H, right? Let's index them, and this will be I-1. So H will be the state of the system as the state. Have HI, which is equal to the whole model multiplied by the vector of the current state of the model, plus some matrix B, which is output matrix, known as output matrix, which essentially tells us how should we modify the input to get the output that we want. But it's kind of just for let's say, yeah, and then we have some vector X. Let's mark it with T. So T is like a time or something. Actually, I think the T is just I. Right. So an X will be our input. In our maze model, the input will be like where they're going to go next, right? And state space models work by calculating the next state of the model by combining the context of what's happening with the input and how that input influences the whole thing.
Is A constant?
What? Yeah, A and B are constants, they're just matrices. And A and B in neural network, when we will apply to Mamba, are actually the matrices that will be trained by the training process.
They are not constant.
No, I mean, they are constant when the model is trained.
You just said you're training them.
What?
You just said you're training them.
Yes, when we're training the model,
yeah.
So when the model is used,
yeah.
The B and A are constant. They're just the matrices.
Yeah, it influences the constants in training, they are the trained parameters.
Yes, they're the parameters we're training. And x is our input, which is not constant. And h will not be constant because it's the state of the thing. Yep.
So like I understand that A is like in this case A corresponds to the maze, right?
Yes, A is the so on this scheme A is this. I use the same values. So A will be the in case of the maze, it will be the kind of the whole maze will be somehow encoded in A.
Do we fix the encoding, or do we just let it be like a 1000 by 1000 matrix of real values and let the network encode it somehow?
I don't know about actual dimensions.
I mean, do we like is a task specific?
No. I mean, it is. So we initialize them randomly, train the model on some things, and then whatever they came out to be, they came out to be that.
All right. So like in this case, I don't have to say that A is such that like 0 corresponds to empty cell. 1.
No. You they're initialized randomly, so they're essentially like matrices and like transformers, key value pairs, all of that. So they just kind of configure themselves as we train on them.
Right. So
yep.
We have two weight matrices. One weight matrix we apply to the previous state, or like the current state, if you wish, and
yep.
one. Actually, yeah, I think it's kind of more useful to say previous here because like we have previous state plus current input.
Yes.
So like one weight matrix to previous state, another weight matrix to new input.
Yes, exactly. And so we get the new state, and then when we have the next input, for example, if we're processing sequences, the next token, right? Then this whole process repeats, and we can always have our updated state in language that will be the context that is happening in.
Yeah. So far, this this is an RNN, as I understand it.
Yes, this is very similar to RNN currently. The thing is, there are also a C and D matrices, but they're kind of irrelevant. They are just some not hyperparameters, but they're relatively unimportant to this whole idea. This is similar to RNNs currently, and Mamba is just based on them. The thing that Mamba does is, first of all, it incorporates some ideas from the long-term short memory networks that are extensions of RNNs, which solve some issues with short-term memory of RNNs. But the key thing that they solve is that this kind of principle can then be applied, actually implemented, in two ways. So there are actually what time is it? It's fine. There are actually two key takeaways from here. So, what are the two possible ways of implementation of this thing? First, as you rightfully said, we can do it as recurrent neural networks. So, for example, to calculate token I equals 7, we calculate the first, then we from it calculate the state of the second, and do it all the way linearly. We can also use approaches from concurrent neural networks. We can have some, because this all is matrix multiplication, right? What we can do, we can essentially write a kind of vector, also called kernel, in which we will have, let's say, B here. So this is just a vector of values, right? Of B here, BA here, BA squared here, BA third here, and so on. Right? So we have this vector because this whole thing is completely kind of deterministic, and what the arithmetic thing will be at ith iteration, we can pre-calculate essentially what this whole thing will be in the end multiplied by, and we can store it as a vector, and we can then, when we have our sequence, let's say we have another vector, right? This is the sequence we want to process, or say train on. And we have some x0, x1, x2, xi, xn, right? And it's the length. So we can then kind of apply this vector as just in parallel.
Can you write the update equation for the previous part again?
Update equation? Yeah, sure. So hi is a hi minus 1 plus bxi. This is the update equation. So then we have this vector. Instead of going one by one, as in recurrent neural networks, right? We can apply this vector to these four, then shift it by one, shifted by one, shifted by one, and so on. How we do it in concurrent neural networks, right? The issue of this approach for actual inference when we want to use the model is that our context size is limited by this very thing, right? Because when we move it, it immediately loses the context of the very first thing. But this process allows parallelization of things, because instead of computing everything in linear time, we can essentially just have, if you have a lot of CPU, we can.
Why are we limited by context lengths if we have b and a and they are constant and we can compute them as needed?
Because what we do is we have. Can you repeat the question?
Yeah, so we have two constants, b and a.
Yeah.
We want to multiply those vectors. Okay, so what do you want to multiply by what?
So this is our sequence of tokens. We want to calculate the output for each token, right? Because the system is kind of predefined in this way. For example, we can calculate this thing by so actually, how to say it? So we take these four, right? Take these four. We have this thing. We calculate the context for this one, right? Using just B. Then we can calculate context for this one, and we can because this one is based on the context from this one, we can essentially calculate first step of these four in parallel. Then we can calculate these three in parallel. Then we can calculate these three in parallel, and then we all only good with this. So instead of having all of them back to back, we can on GPU.
So like
do parallel matrix multiplication thing.
So do I hear you correctly that we first we what exactly do we multiply by what here?
That's a good question.
We can skip it. It's fine.
No, okay.
All right.
I mean, I do understand it, but I don't understand it well enough to explain. I think
it's fine. I can ask it in another way. So you say that we are limited by the length of the above sequence, and like, I mean, all right, but like, is this an efficiency consideration? Because like, let's think about, like, consider that B and A, if they were numbers, not deficits.
Okay.
Then, like, what we have here is a function which says f of x b times a to the x.
Okay. Yeah.
And this is a constant time function. Like, this, you don't have to pre-compute it. You can just compute it.
Yeah.
With any given x.
I mean,
so in what sense are we limited by x?
Because we still, I mean, if we have this formula, right? Let's write h2. Okay. Actually, I think I've written it confusingly. So if we write h2, right? We pass it here. We get a hi minus 1 plus bxi plus bx. Oh, so this is
I plus 1.
I plus 1, yes, and this is I plus 1. I plus 1. I plus 1. Right? So this is what the next step will be. As you can see, we still need this thing. So, but we'll have h squared.
What thing is that thing? You mean h?
H. So we still need the context for the very first thing.
Yeah.
But we can parallelize it by having matrix multiplication here, calculated in parallel on GPU, and this thing, the summation. So this whole, if we expand it, right, we get a squared hi minus 1. And for this thing, we actually need the very first one. But the a plus bxi plus this thing actually doesn't.
I think it's not a plus, it's like just a b.
Oh, yeah. It's a b, yeah. So, but this thing doesn't depend on any of the previous steps.
Yeah.
And this thing can be computed in parallel with this.
Yeah, sure.
So this heavily optimizes on GPU and allows us to do the parallelization equal in efficiency, almost equal in efficiency to what transformers are doing.
Yeah, I mean, sure. Nice algebra.
Yeah. The thing is, because we have like in when the size of this, so if the size of this context of this kernel is equal to the length of the sequence, then we have basically the n² complexity of transformers, right? Because we have to compute for every single one. We have to compute this. But if you have them smaller, then this n² complexity doesn't really come into play. And we can actually, so when we implement it this way, instead of having like recurrent networks from the previous step, we have fast training, but we're bad at inference time, like with transformers, because either our complex is very small, or when it grows large, this thing becomes expensive to compute for every single token, right? So what we can do now with Mamba, and this is the whole purpose of doing this whole state space and this matrix algebra, is that when we're training and we don't really care about the context size, and we are mostly concerned with how fast we can compute and like use our GPUs, we can use this implementation. And then we use the matrices now trained, take the same matrices and use them in the previous approach, which is based on recurrent neural networks. And we get bad training, but we don't care about training anymore. And we get very fast and kind of efficient inference. So when we train the networks, we use this one. When we then use them, we use this one. And so we get best of both worlds because the underlying matrix can be kind of used in either way. This is kind of the main takeaway of this whole messy speech. The last thing about what they do, what Mamba architecture does, is they use selective, actually, state space models. So the issue with RNNs, if you remember, I was talking about it, is that they forget the context that was long ago. And we can kind of have, this is like 3 minutes, just the last point. So Mamba steals an idea from long-term short memory RNNs. And we can draw this kind of line, which is context size. And we have transformers here, which are just full n squared. Then we have recurrent neural networks, which are one-dimensional and vectors. And what the Mamba does is based on the input. So it takes the kind of size of the input as one of the parameters to its A and B matrices when we're training. So we also use the kind of the input themselves as one of the parameters. So what it does, it takes kind of the middle ground between them, between the transformers and these, and what it achieves is basically it. So transformers keep a lot of relevant data because they have the full context size and size, right? They keep all the like ums and ems and useless words and everything like this. RNNs instead have only kind of the closest ones. What Mamba does, it has long-term short memory algorithm to pick out only relevant things and to keep only them in context size. So it avoids the kind of fundamental flaw of transformers where they spend a lot of computation size on multiplying vectors by like zeros.
What exactly is that? Is it like a learned, so how exactly does it work? I mean, there are just a few ways to implement that.
What?
There are just a few ways to implement that.
Yes. As far as I understand it, the original implementation of the paper, how they do it is they, when they're training the model, they take the input. So they have the token of the input as like the thing they're inputting, but they have some kind of hyperparameters of the input as parameters kind of fed alongside the input to the model.
Like an index.
In simplest way, just length of the input, for example. And then they kind of check, depending on what kind of input the model gets, which parts of the context are relevant, and train model on that. So it tries to only keep in its, so it dynamically adjusts the context size based on the input. So for example, if your whole context is like very relevant, it will try to keep most of it. It has like some kind of sigmoid thing where it kind of determines, because it doesn't want to get all the way here, we will lose our efficiency. But it kind of dynamically moves depending on the input you give.
All right. So it's like a learned something which activates or deactivates like parts of.
Yes. So it kind of selects what kind of matrix you will use for your context. And for each token, this matrix will be different, kind of avoiding doing self-attention heads process. So this is Mamba. It is very cool. And it was released in this winter, like the foundational paper. And I haven't actually seen since then it to be yet used in any like big models, and I'm not sure why, but I think that there are a lot of papers being released since then. I think it will be very cool in some. Oh yeah, and the actual original paper also has a lot of evaluation, and this thing is like, it really does all that it says. It is fast. They haven't, of course, checked it on like 5 trillion parameters models because they can't train them. But on like billions of parameters, it trains much faster than transformers, and works sometimes even better because of the selective context thing.
Yeah, so I am confused and I have two questions.
You go.
So I don't understand what state space models are, and in what way what we talked about is a state space model.
Okay.
It's like my current understanding is that we talked about a scheme where we take an RNN, we take its update equation, and we employ the kernel tweak. I mean, like, which is alright, but I have no idea how this connects to state space.
State space. I kind of I understand myself, but I think I should consult the paper to give you like a robust answer on this.
Yeah. It's not like. Is there any particular reason like so? I just want to say that like if you consult the papers, you can see that like I don't know, people release approximately 10 new architectures per month.
Yeah.
Is there any particular reason you think this is the one?
Well, first of all, I read a bunch of it, and I think that I don't think this is like I can't say with 100% certainty that this is like the future and transformers will forever be like whatever. But they show kind of strong evaluations in their paper, which not a lot of architectures do, and most of the architectures are like, this works, but we don't know how well, or actually doesn't work that well, or like whatever. They have strong evaluations regarding some like more like foundational simplistic tasks, which like smaller models can do, and they do show that they outperform most of the kind of currently in use architectures. So I found that convincing. And also they rely on a lot of work which has been used as the foundation of currently like SODA architectures, which kind of gives a bit of confidence in Mamba, because like if SODA architectures use these things and they're proven to work well, and Mamba uses them as well, like okay, transformers work on convolutional neural networks, at least like based on them. Mamba works on similar well-proven concepts. So that was the second kind of reason why I looked into Mamba, and I find it promising. Yeah, and just in general, I think most of the time we get promising results in some field when we take some like well-researched things from other fields, like for example, state space models, which are well known in mathematics, and then we can like, how can we apply this stuff to here? And I think that's what Mamba does.
I'm skeptical about whether this works in machine learning, but with it.
Yeah, but first 2 points are main reason why. Also, being honest, the reason, like the top one reason, is just because I was like, oh, that's some cool math in there, like algebra and things, and everything works beautifully. So I was like, I'll share with you guys. It's not like I will invest my next 3 years of life into researching Mamba. The same reason I picked the weight initialization, because it was like, oh, some fun distributions and things. But yeah. I honestly want to refine a presentation on Mamba and maybe even I could give some lecture in my university about it or something.